Hey everyone, this is MAT 221, Calc 1. We're into section 2.2, which is talking about the concept of a limit of a function. Here we start talking about the actual calculus of the course and this concept of a limit. So what exactly is a limit of a function? Let's start by looking at a table of values. And as we saw in the beginning sections of review, we're going to be talking about looking at things this semester in 4 ways. And the first of 4 ways is numeric, which is looking at tables. We're also going to look at Mathematica to help us as we move through the semester. But here, let's look at this table of values of the values of the output of the function f of x for values really close to 2 but not equal to 2. So if we look at this side of the table, we see that our input values are on the left side of 2. In other words, at x equals 1, at x equals 1.5, 1.8, 1.9, 1.95, and so forth. Notice getting closer and closer to 2 from the left-hand side of 2 on the number line, yet not quite reaching 2. And this column of values shows us the output of the functions. What this is, as the input changes getting closer to 2 from the left, what happens to the output of the function as we come. So as we get closer and closer to 2 from the left, our output of the function, we notice, is getting closer and closer, looks like, to an output of 4. Now let's look at the other side of 2, where we start on the number line at x equals 3, and get smaller and smaller and smaller, getting closer and closer to x equals 2 from the right side of 2. So notice our input values are getting closer and closer to 2 on a number line, but not getting exactly at 2. What happens to the output of this function that we don't know what the function is yet? Well, we look, the output of the function is 8, then 5.75, and so forth. What's happening to the output of this function? The output of this function is also getting very, very close to 4. This is the beginning of our idea of what a limit is. A limit is a targeting output value of a function. What is the output of a function targeting as the input is getting closer and closer to a given input value without ever having to actually reach that value? This is showing us that the output value looks like it is getting really close to 4 as x is approaching 2 from both the left side of 2 and the right side of 2. All right, so what does this tell us? Well, from the table, what I did is I made a graph of the function that I was talking about, the graph of f, which happens to be a parabola in this case. And you can see from the graph, and again, remember we're looking at things numerically, which is in tables. Then we're going to look at things graphically, so here's the graph. Then eventually we'll look at things analytically or using algebra or symbols, and then we'll verbalize what this means. But now let's look at the graph in figure 1. If you notice, if we put x input values of, say, 1, the output would be this. 1.5, the output would be here. 1.8, the value would be here. 1.9, the output would be here. So notice, as I come in from the left side on my input values, my output value is targeting an output of 4. Same thing on the other side, what the table showed us was as we came in and got values of input values closer and closer to 2, say 3, then 2.5, the output would be this value here. At like 2.25, something like this, 2.1, the output with this. Notice as we come closer and closer from this side, my output value is also targeting an output of 4. This is the concept of a limit. This is why I use this target symbol. A limit is simply the targeting output of a function as the input gets closer and closer to a given input value. The limit is telling me what the target is. I don't actually have to reach an output of 4. I just have to target that value. Now notice in this particular function, the function actually does hit that target of 4 when x equals 2. But the concept of limit, we don't have to hit that value. We just come closer and closer to 4, an output of 4, as x gets closer and closer to an input of 2. In fact, it appears that we can make the values of f of x as close as we like to 4 by taking values of x significantly close to 2. We express this by saying the limit of a function, f of x in this case is x squared minus x plus 2, as x approaches 2 is equal to 4. And here's our notation for a limit. So we say the limit of this function as x is approaching 2 from both sides is approaching an output value of 4. In this case, it actually reaches 4, but the limit notation and the limit of the concept of limit is we don't have to say that it actually reaches that value, it just targets that output value. Notice here when I say as x approaches 2, here's the notation for the limit, it is implying from both sides, from both the left side and the right side. So here's our general definition for a function and a limit. We say that the limit as x approaches a of a function f of x is equal to some number L. The limit as x approaches a is equal to L. If we can make the values of f of x really close to this some number, in our first case was 4, as close as L as we like, by taking x values really close to a on either side, but not equal to a. This says that the values of the function tend to get closer and closer to the number, some number L, in this case 4, as x gets closer and closer to the input value of a, in our case 2, from either side, but not equal to that value. Here's an alternate notation for function that is sometimes used, rarely, but sometimes is used. Instead of using this, which is the classic notation for the function, the limit as x approaches a of f of x equals L, sometimes it's written like this, f of x approaches L as x approaches a. Notice the phrase, but x is not equal to a in the definition of the limit. This means that we're finding the limit as x approaches this number a, but we'd never have to consider the actual value at x equals a. In fact, we don't even need to know if it's defined there. Only thing that matters is how it gets there close to it, its targeting value. So remember, the limit of a function will refer to the value of the function, the output of the function, what that output is approaching, but it does not have to be the actual value, even if there is one. So let me give you an example graphically. So here is a function. I'm sorry I didn't define it as a function, but this is a piecewise function. It's defined in pieces. It looks like a linear function up to 2, then it has a dot at x equals 2, and then it has a constant function from 2 on. Okay, so here's some questions. What would be the limit as x approaches 2? So let's look. I say it equals 2. What we would do is we start over here at the left of the function, and we approach this value. So we approach at x equals 0, the output of the function is 1. At x equals 1, looks like the output of the function is 1.5. As x is approaching 2, my targeting value here is an output of 2, even though the function is not defined at that open circle and it is actually defined down here. My targeting value as x approaches 2 from the left, I'm targeting a value, an output of value of 2. As I come in here from the right, again, my targeting value is equal to an output of 2 as x approaches 2. Notice the actual value of the function. If I said to you, what is f of 2? You would say f of 2 equals this solid dot, x equals 1. Excuse me, y equals 1. But it is not the limit. For a limit to exist, the function must approach the same targeting value from both sides. So notice I'm targeting an output of 2. I'm targeting an output of 2. The value of the function is equal to 1, but it doesn't matter. I'm just, what is my limit is, what is my target value as x approaches 2? One-sided limits can also exist, and they approach from either the left or the right side, and they have a special notation. One-sided limits, we use a special symbol after our approaching symbol. So the symbol x approaches 0 with a little superscript here of a negative sign is indicating that we consider only values of x that are less than 0, or in other words, coming in towards 0 from the left. This is called the LHL, or the left-handed limit, because we're coming in from the left side of 0, or the negative side of 0. Likewise, the notation x approaches 0 with a superscript of a positive indicates that we consider only values that are greater than 0. This is called the right-handed limit, or the RHL. We're considering only values coming in from the right, or in other words, from the positive side of 0. And here's our limit notation. The limit as x approaches a is equal to some number L if and only if the left-handed limit, in other words, coming in from the left, and the right-handed limit both agree that they are targeting that same output value of L. So again, let's look at some examples. If I said to you, what is the limit as x approaches 1? As x is approaching 1, we look and say, okay, we'll start here. Here's x equals 1. We'll go on the function and say, okay, what is the output of the function targeting? What's my targeting output value? My targeting output value is equal to 0, y equals 0, when x gets closer and closer and closer to 1, but never has to reach 1. I'm just targeting what value this is targeting toward. It is targeting, the function is targeting an output of 0. That would be its left-handed limit. What about as we target from the right? So as we come this way toward x equals 1, here's x equals 1, we ride on the function and say, what is my targeting output value as x approaches 1 from the left? My output value is approaching 1. Here's my output value. That's my right-handed limit. So my targeting value as I come in this way is targeting an output of 1. But these two targets do not agree. And the limit definition says that my two limits, my left-handed limit and my right-handed limit, must agree in order for the limit to exist. Therefore, I do not have a limit here. The value of the function, f of 1, is the solid dot here, but the actual value of the function, the limit of the function, does not exist because my left-handed limit and my right-handed limit are not agreeing with each other. Even though the value of the function exists, I have a solid dot right there. If I said to you, what is f of 1? F of 1 is the solid dot right there. My targeting values here as I target from the left, as I target from the right, are targeting two different values. Therefore, we say this is a DNE, or does not exist. Now what about at x equals 2? At x equals 2, as I come in from the left, my targeting value is targeting an output value of 1. Even though the value of the function doesn't have a value there, I'm still targeting an output of 1. As I come in from the right, my value is targeting, again, 1. The value of the function is the solid dot up here at x equals 2, but it really doesn't matter what the value of the function is because a limit is simply a targeting value. So I'm targeting an output of 1 from the left. I'm targeting an output of 1 from the right. Therefore, my limits are both agreeing, and therefore my limit exists even though the value of the function does not equal the value of the limit. So here we say the limit as x approaches 2 is equal to 1. Let's do one more really quickly here. At x equals 3, my left-handed limit targets 2. My right-handed limit targets 2. My value of the function also targets 2. Just happens in this case, the limit as x approaches 3 is equal to 2, which happens to equal the value of the function.